So our project name is Locking Processor, Hardware Performance Counter, HPC, and Malware Detection. My name is Sumita.
My name is Hashim.
My name is Varun.
My name is Dylan.
And my name is Alec.
So the motivation behind this project is because with the rapid growth of malware, with almost 1 million new malware files being created daily, the need for malware detection systems is high. And the traditionally used software methods have proven to be pretty ineffective against the newly developed malware. This is because they require constant updates just to keep up with all the new types of malware that's developed. It's really hard to constantly update the algorithms associated with these, and it makes it hard for them to be effective on their own, while software-based strategies rely on constant updates of databases to account for new malware. A new method using HPCs have been found to be pretty effective against new forms of malware, and this is because they monitor the constant state of the CPU rather than specific algorithms. So our project objective was to explore the effectiveness and use of HPCs, which are hardware performance counters, for malware detection. So just to provide some background and terminology, malware refers to any sort of software which is designed to tamper with a device in an unauthorized way. Traditionally used software antivirus strategies employ algorithms and database information to detect malware. A hardware performance counter, or HPC, unlike the traditionally used software methods, is built into the CPU, which is the central processing unit. And HPCs are effective because they count cache hits, misses, branch mispredictions, and CPU cycles. So whenever malware is deployed, it's going to cause the hardware to behave abnormally, and this is how you detect the malware on behalf of the HPC.
All right, so with that, we can move into the methodology section of the project. Basically, how we implemented this is we actually created two computer programs in C++. The first one, which is our benignware, was hospital.cpp, and that was a hospital database file with a bunch of functions, and it has like some sensitive data. And we actually password protected that with the 4-digit password that we set. Malware.cpp is actually our malware in this case. And basically, what it does is it's a random number generator that brute forces the 4-digit password in the hospital database. Um, and so the reason we have this setup is to show that with our benignware, you're really going to only have to enter the password once or maybe twice if you forget it. Versus with our malware file, it's going to take thousands of attempts, to get that correct password for the hospital database. So we wanted to show that hardware activity spikes with the malware, and it doesn't with the benignware. Here's a little bit about the hospital file, the hospital database. You just, you run it, and then it prompts you for the 4-digit password. If you enter the incorrect password, then it'll exit the program. And if you enter the correct password, then it'll grant you access to the database, and then you can enter the choices from there. So you can see here it took 2 attempts to enter the hospital database because the user actually knew the password. And this is our malware right here. When you run the malware program, it gives you a message saying that the malware has been activated. And then it basically uses a random number generator to brute force that 4-digit password. So it found the password 2024 after 8,970 attempts in our first trial, and then 1,094 attempts in our second trial. So as you can see, this is taking thousands of attempts to find the password versus just 1 or 2 attempts in the benignware. So the goal was to show that, there's a lot more hardware activity here.
So once we got our programs all put together, we were able to load them into the VM and began tracking the hardware counters. So our first attempt, we started out using perf tools, as can be seen by the screenshot below. But due to some of the limitations with the VM, we weren't able to get all the information. As you can see, it says not supported for instructions and branches. To solve that, we used the Valgrind tool. We were able to get some better insight into the data. So once we got our methodology figured out, we were able to do a couple trials. The graph at the bottom of the screen shows 5 trials that we did. And over to the right, you can see some of our sample results. At the top is the benign-ware, the bottom is the malware. And as can be seen, the malware has significantly more instruction references, which heavily implies that the malware is using more system resources, which is pretty able to see when tracking the hardware counters. And the more tests that we're able to do, the more sure we are that we are dealing with malware.
To continue with the results, we have so with the malware, it happens because the brute force method used by the malware is highly repetitive. It runs thousands of loops trying to guess the password, which leads to a much higher number of cache accesses compared to how the software normally operates. This constant guessing process puts extra strain on the system and increases activity far beyond regular usage. On the discussion portion of it, there's some pros and cons to it, and the HPCs allow for real-time monitoring of CPU activity with minimal performance overhead. It's cost-effective, and it's as executing the methods of this project require no spending, and the HPCs detect anomalies in hardware behavior. Updates are not necessary. On the negatives, HPC readings can vary from background processes, resulting in false positives or false negatives. Also, they're unable to pinpoint the exact malware responsible for the extra CPU usage. In most cases, a combination of malware detection methods must be implemented to find what malware is being used.
For this assignment, we gained technical proficiency in not only testing malware and benignware to distinguish them apart, but we also used VMware in order to simulate a controlled environment in order to conduct testing on our programs. While testing, we utilized Linux tools such as perf and Valgrind to measure hardware performance, and we gained experience using a real-world application of detecting malware rather than doing it hypothetically. We showed a simple practical implementation of hardware performance counters to demonstrate the difference in performance between malware and benignware. We also showed that instruction references, hits and misses, can be a good metric when determining malware from benignware.